So what chapter are we on? 8. So I'll knit this and then we can just go through that.
Now, are you working from some resource that you found, or is this something you've put together yourself? You said you're knitting.
So there's a guy called Solomon Kurtz, and he basically has converted all the stuff in this book into tidy modeling.
Oh, nice.
Into tidy format.
Now, did you say his name's Solomon Kurtz?
Yeah. I can share. I can actually. I'll tell you what. I'll put in the chat. There's a GitHub.
Oh, nice. Okay.
And you can just pull. Well, you can just pull from that.
Oh, perfect.
So all I'm doing here is just like showing you basically his work, really. And it's just useful to work from because usually we end up having to create our own.
It's nice to interact with it, certainly. So yeah, that's good to have.
Sorry. So it's been a while since I went over it. Since been over this. So and I'm quite happy to go over the maths as well. Actually, in fact, that's probably the part that I enjoy the most because it helps me to understand things a little bit more. So I'm just going to go from the notes list. So this chapter is about fitting regression models, which is pretty straightforward kind of thing that we tend to do. So it says in this chapter we lay out the mathematical structure for inference for regression models, and they'll go over some algebra. We explain this rationale using blah blah. So it's going to go over least squares, maximum likelihood, and Bayesian inference. Now, I haven't actually finished the last 2 pages of this book. It's been quite busy, hopefully we can learn that a bit together. So least squares. So an ordinary least squares model is, basically an intercept slope with which is times by how many of that value you have plus the error terms. So coefficients A and B that they use here. Data point, if the number of data points is n is greater than 2, it's not generally possible to find a line that gives a perfect. So what they're saying here is that once you move beyond, say, 2 lines, typically speaking, you're not going to have perfect fit. But that's good because speaking from the perspective of someone who's working in demand forecasting, you don't never want a model to be perfect fit because then it won't work. But that's what overfitting is all about, really, isn't it?
Yes.
Anyway, the usual estimation is to choose an estimate that maximizes the sum of squared residuals, or you could use the term error, but that's not technically correct because error refers to the exact amount and residuals refers to the leftover from the estimates. I believe that's the difference, which is why you've got the hats on top of the intercept and the coefficient. Model is written in terms of errors, but it is residuals that we can work with. We cannot calculate the errors, as to do so would require knowing A and B exactly, which is essentially what we're saying.
You don't.
The residual sum squares. So the A and B that minimizes the RSS, it's called the least squares or ordinary least squares. I've just got a message.
Is it Pavitra? Wow, there's quite a lot to this repository. That's good, though.
Oh, yeah. Sorry. So the residual sum of squares. So what is that? So residual sum of squares is the sum of. It's just the squared sum of residuals. Pretty straightforward, isn't it?
Mm-hmm.
Yeah. So when we do that, are we attempting to minimize? Yeah, we're always attempting to minimize the RSS.
Yeah.
So in the regression model, the errors come from distribution of 0 and standard deviation of sigma. Why is it coming from a mean of 0? Oh, because we've put a line through it. Oh yeah, because we're taking away from between the actuals and the recorded, aren't we? So that just that converts everything to 0, and then you've just got whatever's left over. Residual standard deviation, mean is 0, definition. Do you understand what XT is?
XT?
Yeah, so you know on page 1103.
Yeah, I'm having a little issue with my Slack window. I'm trying to pull it up so I can see it better. Sorry.
Is this too small?
No, I think it's just the way I've got. Oh, okay, yeah, it's just the way I've got it on my screen.
It hasn't properly rendered it quite. I don't know why, but it doesn't quite render these.
Yeah, my Zoom is
equations
misbehaving badly. I'm going to try to see if I can get this up. Oh, here, much better. So there you are. And do you have your shared screen? It's only showing you. Let's see. Sorry, I'm having issues.
No worries.
Switch to sharing content. Okay, no, I see it now. I'm good. Okay, so the question you were saying on is called the residual sum of squares. That's at 8.1. So what was the question that you were asking then?
Do you know what XT stands for? So if you're looking at the formula, I can't see it here. Where is it?
Yeah, it's rendering very weirdly. Which page is that in the book?
It's 103. So it's the first page of chapter 8.
Oh, gotcha. Okay. XT. Oh, just the transpose of the.
Oh, it's a matrix formula.
Okay. Yeah. So right. It's transpose times X, inverse of that times the transpose times Y.
All right. So sorry, I believe I actually went over this last time with Paprita, but like I always forget that. So basically we can calculate the standard deviation of these sums of these residual values.
Right.
I mean, that doesn't sound particularly complicated to me.
No.
Because what is that? That's just the square root of 1 minus n plus sum of the residuals squared. And it's got the whole formula there anyway.
Mm-hmm.
So yeah, it's basically the same formula, isn't it? But just square root, and then added in the number of samples. Okay. So essentially, what it's saying is, in order to calculate a regression, we have to allow for error, and that what we're attempting to do is minimize the residual square differences, including the the standard deviation of those residuals as well, which must be normally distributed, because if not normally distributed, the theory breaks down.
Mm-hmm.
Right, so compute the sum directly. I mean, we do this in every regression anyway. So it takes x, y, a and b. X and y are vectors, a and b are scalars. So x and so that's your so that's x and y are just any value, I suppose. Mm-hmm. Sorry, y is your predicted value, x is your predictor, I suppose, and then that's your intercept, and that's your coefficient for your regression, essentially, and that should return so y minus A plus B x creates that. Oh yeah, so B times yeah, so that's basically so this is your predicted value, so it's just the actual value minus the predicted value. Okay, you think they could say that? And then this is application of that, essentially, being based on that regression that was calculated earlier on. So what it says here is that that a vote is 46.3 million votes for an politician in the White House, and then 3 million per increase, 1% increase in income or something. Yeah, but it's kind of like, what's it, growth, isn't it? Relative growth.
Right.
Okay, and then they just grow that and plot the parameters. Oh yeah, so this part's quite interesting, isn't it? So what happens is as we go along, so that's our predicted RSS. We might explore the different values of A and B. Yeah, so what we can do is explore different values of A and B, and we'll see what the RSS is. So as we increase A, or change the position of A, then the RSS gets worse, essentially.
Yeah, it shows that it is in fact the min.
Yeah. And then this one is, what's this one? Crossing from 30 to 60 D value of the RSS. Oh, so this is just, so this is a value, this is changing the value of the intercept, and here's changing the value of the coefficient. And what it's doing is it's creating a, what's it? How do you describe these plots?
What is that called? The 2D, it's not a heat map because it's not, yeah.
It's like when you do simulated annealing.
It's like a tile. Yeah, he calls it. Yeah.
It just shows you the part at which it's kind of like when you're doing gradient descent, and it shows you the bit that's the best part to land your parameters in. Yeah. So what it's saying is, right here in the center is the best bit.
They should put red. It seems like there's kind of a broad minimum. I don't know. It doesn't really capture.
It could have done with a cross,
I guess. Yeah. I maybe it's just the scale. I don't know. Yeah.
Yeah, it's not so obvious. I don't think that color system's working too well. Or maybe it's just because it's just too big. Anyway, so anyway, this all amounts to the fact that the largest RSS is found with the same points as we have in our regressor, because the regression naturally picks up on those things because of the nature of that algorithm, which is the whole point, is to minimize the RSS. Now, the maximum likelihood, which is a really annoying concept that I always can't quite get my head around. Well, I can't. Right. So if the errors from a linear model are independent and normally distributed, which we should hope that they are, so that yi as a function of n times a plus b sigma squared, least squared is also the least squared is also the maximum likelihood estimate. Oh, sorry, is that kind of what that's showing? Is that what it's saying?
Careful study of, blah blah blah. Yeah, I think it's just saying that it does end up being equivalent to sum of squares, because although you're multiplying out the likelihoods, they're exponents, so you're actually summing them all. So yeah, I think is why that ends up working out. That's how I interpreted it anyway. Yeah.
Yeah. I saw a stat quest on this not that long ago. It's one of those concepts that's really important that I always completely neglect.
Yeah.
The likelihood function of regression is defined by the probability density of the data given. So that's very important for Bayesian, isn't it?
Yes.
Because it's the likelihood function, the likelihood that we have found the right, I suppose, the right parameters.
Yes. It's kind of like how well does the data, or yeah, how well does the data support the parameters, perhaps. Yeah.
So if we were looking at a Bayesian approach, the maximum likelihood might be a best approach from doing lots of simulation to basically make us question the parameters so that we've got some variance in parameters and we find the optimal one out of the simulated conditions. Or I believe that's kind of how we would approach it. Right. So where do the standard errors come in? Using careful likelihood reveals maximum likelihood requires maximizing some of residuals. Minimizing. Sorry. Hence, the least squared estimate that the beta is equal to alpha a hat b hat could be viewed as the maximum likelihood estimate. The probability function. Right, okay. So 1.5, what's this? Where do the standard errors come from? Using the likelihood surface to estimate the uncertainty of the parameter estimates. So this is kind
of... This looks a little better, yeah.
Yeah, this is better, isn't it? This is basically, was it A1? Sorry, I mean figure 1, 8.1a. in the book. So that's saying, was it likelihood?
Oh yeah, he has the nice little mountain there showing the likelihood.
Yeah, the log likelihood estimate. Well, because it's normally distributed when it's log. So it's log normal, isn't it? Combination returns the also 2. Okay. This will serve as figure 8 based on distribution. Here's the maximum likelihood. The authors have not yet covered the maximum likelihood standard errors, so we aren't in a position to make versions of figure 1.A1b or 6.1c, but we can make the figure 8.2. So what's it saying here? So this is just bring us back to the old data. So it's just the regression. Yes. So this is perhaps a more interesting part from the Bayesian point. So this is what's it? Map of these are a range of all possible linear regression fits. So how did they do this? What was this magic? We used what's it? BRMS posterior samples function to draw as many from the posterior distribution of the model. That left us with a column for each of the 3 parameters, which is this output called b-intercept. We then use slice example to take a subset of 50 rows. So
yeah, in statistical rethinking, you'll see a lot of plots like this, where they sample the posterior distribution to get a sense of, I guess here we're just kind of seeing that, there are a lot of possible fits. We have a best one, but we have all these others that kind of vary from that.
So posterior samples takes the model and then just replicates the sorry, hang on. So we take a Bayesian model and then posterior samples draws posterior distribution model. So is it creating new distributions and then drawing lines through it, or is it just creating different lines based on different samples of the data?
The way I understand it, it's kind of when you're doing these kinds of fits, they will sort of traverse kind of the space of the possible parameters. And, you know, depending on how good the fit is, it will kind of guide it so that some will come up more frequently. So yeah, so when you get ones that are close to what you see above, you'll see a lot more of those in your samples than you'll see, you know, wild things like the one that's nearly flat. So it's just kind of, it's a reflection of that, I believe. Yeah.
Oh yeah, sorry. So it is.
Yeah, it kind of goes back to the Markov chain Monte Carlo, and yeah, that's a fun thing to have a look at, kind of how that all works. But my understanding is, yeah, that's what's kind of going on there. Yeah.
This is making me think of what's it called, random forest.
A little bit, yeah.
Where it takes different kind of like sampling of the database,
right,
and then just basically builds a decision tree, and then builds another decision tree based on different sampling, etc., etc.
Right. So yeah, there's the bootstrapping going on.
Exactly. Yeah, that's the phrase.
Yeah.
Exactly. Right. So that's left us with column, and therefore, like, we can see that it's slightly thicker in the middle where we'd actually expect to see the real line, which is basically this bit here. So that kind of conforms to this idea that, oh, as we get wider from the distribution, it becomes less sparse. It becomes more sparse.
Yeah, and then it does give you a sense then also of the uncertainty, just that because you don't really have a lot of data, you could get, you know, these other fits as well. Yeah. Whereas if all the data were on a line, it would just be just this, you know, dark streak in the middle.
There's not much certainty there, but I imagine that there's not been many elections in the history of America.
There have not been many elections, so only every 4 years.
Yeah. So in this case, it's only 16.
52, yeah. So 62, that's a pretty small sample size. But you know, but then you think, well, with only 16 points, that's actually pretty impressive fit. I don't know. It indicates there's something there, to me anyway.
I certainly agree. I mean, the economy is always the win or die of anyone in politics. That's why they're so bothered about the stock market.
You'd wonder if there wasn't a relationship, you'd say, what's going on? But yeah, no, for sure.
Exactly, right. So we've got through that. Right, so now we get to the Bayesian invariance part. This is the part that I haven't, I've started reading.
Yeah.
But I have not read the last 2 pages. So, so the posterior sample things, that's really cool, actually. I really like that. Do you know what this bit means? We also got a column IP is currently out of scope, but we can look back at the B-incept.
Yeah, I do not know what that is. I would have to look that up myself.
This is, look, I've heard this term credible interval.
Credible interval.
And it's all about, you can look at the B-incept as a collection of credible A values and B column as a collection of credible B values. So they're saying how credible it is. I presume. I don't really fully understand what that means statistically. This is the problem, is sometimes they introduce stuff and it's like you end up debating this and it's like, well, that's introduced later on. But anyway, we'll crack on.
Go ahead. Yeah.
Least squares or maximum likelihood finds the parameters that best fit the data, so essentially we can say that they're basically 2 sides of the same coin. According to some pre-specified criterion, but without otherwise constraining or guiding the fits. But as discussed in section 9.3 and elsewhere, which we haven't got to yet, we typically have prior information about the parameters of the model. Bayesian inference produces a compromise between prior information and the data, doing this by multiplying the likelihood with a prior distribution that probabilistically encodes external information about the prior information. The product of the likelihood in the above example is P Y or A, What's this? What's this symbol I mean?
Probability of y given
A.
that your parameters are a, b, and that you have the standard deviation.
Oh, right. Probability of y given a.
Yeah.
Oh, the probability of y given all three of these.
Given all of them, yeah.
All right. I would have see when I'm reading it like that, I'm reading it like this.
That and then the two other things. I see.
Not like that.
Yeah, gotcha. Yeah.
Yeah. In consideration of function blah blah. So what's the probability of y given intercept coefficient and the residuals errors? And the prior distribution is called the prior distribution. Summarizes our knowledge of the parameter. It seems stupidly simple when they write it like that, but I don't know. Summarizes our knowledge of the parameter. Prior distribution is called the prior distribution, and it summarizes our knowledge of the parameter. So what we're saying is we have what we're saying is that we are able to predict y given a, b, and sigma, but that we have a probability of, we can say that there's a probability attached to that y value. And therefore that there's some error in that, and that can allow us to extract out the distribution in order to test out the parameters, is essentially. Is that right?
Yeah, you start with your prior, you look at the data kind of guides, your distribution. It can move it, make it reduce the error depending on your data.
So if we add more information, we can update the model, I suppose.
Right. Yeah. So that's why they talk about the data. Sometimes the prior does not matter so much because the data is so strong, it just totally swamps the prior. But then kind of what I'm picking up from, some of the things he said is if you don't have a lot of data, that's where this kind of approach can really shine if you have good information to build a prior, because the prior can then keep it from just going wild and having this huge interval so that you don't really you aren't really even able to draw conclusions. So that I feel like that's kind of one of the benefits of a Bayesian approach, is to deal with situations where you don't have a lot of data, perhaps, or can't get a lot of data. Yeah,
that's pretty powerful idea.
Yeah,
I like that.
It feels like you'd have to be very careful though, because then the prior would have a lot of influence. So you would need like some kind of subject matter expert or something, to kind of guide your decision making.
That's one of the things that they're arguing, though, isn't they?
Yeah.
Which is that in many cases we already have a lot of information. I mean, particularly in the era we live in now, there is a lot of information available, and we should be using it rather than just modeling from scratch.
Yes.
So that's what Bayesian inference is. Compromise between the prior information and the data. So by kind of remodeling it all. So pointwise estimate mode-based approximation and posterior simulations. So for the least squares solution, a point estimate that represents the vector of coefficients that provides the best overall fit to the data. For a Bayesian model, the corresponding point estimate is the posterior mode. Sorry, I just need to highlight that because I did not think that was that important. Posterior mode, which provides the best overall fit to the data and the prior distribution. So that's basically saying if we're fitting a regression with Bayesian approach, then it's a posterior mode rather than a point estimate. suitable fit. But is that the same thing as the regression line? So is our predictive line or model, called a point estimate in parametric, and in Bayesian it's called a posterior mode, or is that just a slightly different thing?
I think corresponding point estimate is a posterior mode. Yeah, because in that case you're using the posterior and you just want to find the mode of that.
Okay.
So yeah.
So the least squares, or the maximum likelihood estimate, is the posterior mode corresponding to the model with a uniform or flat distribution.
So basically no an uninformative prior. Yeah, just anything is possible.
Right, okay. Oh, so it's saying there's no, sorry, so is that saying that there's no variation? It doesn't consider any variation, and there's no variation across the error terms when you use a point estimate?
I think it's just saying that, yeah, it's just kind of saying that if you use the flat prior, the answers are equivalent, I think is what that means.
Yeah. Oh, right. Yeah. The probability of the priors are all equal.
Right.
Yeah. Okay.
Because you haven't exerted any influence on it other than, yeah, essentially it then goes back to, what is the maximum likelihood, I think, at that point.
Probabilities of priors is equal in parametric. Right. We do not want an estimate. We want uncertainty. Okay. Emphasis on uncertainty. Influence of individual points in fitted regression. Right. So this is essentially just showing us residuals. It's not clear where this data came from. We'll have to blah blah. They made it up. So essentially, this is showing us just a normal least square slope. I see.
Yeah.
So, if we were taking it from the one above, it would just be the distance between those lines. So when we're calculating residuals, we're turning it into a mean of 0, aren't we? And that's essentially what this is essentially doing.
Yeah.
Okay. Increase of 1 in y corresponds to change in beta that's proportional to xi minus x bar, which is the average. If xi equals x bar, the influence of the point is 0. Yeah, if it's above, it's positive. If it's below, it's negative. Yeah, pretty straightforward. Least square slope as weighted average of slope pairs. We can interpret the estimated coefficient of b hat as a weighted average slope in the data. And we can interpret the underlying parameter b as a weighted average slope in the population. Yes, okay. It's just a different way of interpreting the coefficient.
Right.
Right, so I think so this is almost as far as I got. So, but feel free to jump in at any point, by the way.
Okay, sure.
The base RLM function corresponds to the OS criterion. Throughout the text, Gelman highlights the stan GLM function, which is part of the stan package from blah blah blah. The package emulates other R modeling functions but uses stan via the stan package for the backend estimate. The primary target audience to use it would be open to Bayesian inference if using Bayesian software were easier but would require frequentist software. Wait. Primary target audience is people who would be open to Bayesian inference if Bayesian software were easier but would use frequentist otherwise. Yeah, okay. Fitting models with stan is also useful in experience, blah blah. So you've done a bit of modeling with did you use, when you're using the statistical rethinking, were you using Stan or were you using BRM?
Was using Stan. So the way he sets it up, he actually has his own package, and it's called Rethinking, and it really wraps Stan. So you can define models in your R code, which are then, you know, passed along to Stan and compiled, and then it you know, runs the fitting from there. In this book, so in Regression and Other Stories, he's using that Stan GLM, which appears to be even simpler because in statistical rethinking, you explicitly say, you know, this is a binomial distribution with these parameters, and this is this, and I want to use an exponential probability distribution for my standard deviation, stuff like that, which you apparently can do with the Stan GLM too, because I've read a little bit ahead. But it seems to me so far that Stan GLM and this RStan arm is kind of a quicker way from point A to point B. But the other approach, or, you know, if you really wanted to get into the weeds and learn how to use Stan, then you have a lot more control over your models, but you might not need that much control. You might be totally fine to fit, you know, kind of your basic regressions or your basic generalized linear models. So it's just, I guess, you know, his point about people would use it if using it was easier. I mean, that is what, you know, one of the main things it does is it makes it a lot easier to use those tools than having to go and learn, you know, all the specifics of how you would create a model in Stan and then fit it.
Yeah, I mean, it seems when you're from a frequentist background, you automatically think like a frequentist, and to move away from that too quickly is quite difficult, I think. It requires a whole way of thinking.
It takes some time, yeah.
It's a bit like
I'm interested in this BRM package because I'm not familiar with that at all. So I'm glad this guy is explaining that a little bit here. British Racing Motors.
That's just Google just automatically making bad assumptions. Because I'm British and it thinks that I want to look at British racing motors. Right, so I suppose this would be the best thing to look at. Yeah. So what do they call it? Package implements Bayesian multi-level models in R using probabilistic programming language Stan.
As well, so that's good.
A wide range of distributions, links.
Oh, you could do survival models, ordinal, quantile, zero inflated. Boy, this looks very useful.
Yeah, well, I mean, you can basically do anything. I mean, if you want to see something really cool, Bayesian time.
Oh, time series.
Yeah, it depends on whether you do time series or not. But
I do. So this would be interesting to me.
So where is it? It's model
a lot of time series in my life.
GitHub. Right. So there should be a link on here to some of the other ones. Where is it? Model time. Backtesting. They recently released a Bayesian version of this, essentially. Some of the stuff he does is a bit kind of like salesy.
Yeah, this is that Matt Dancho guy, I think, that does this.
Yeah, but honestly, is one of the best one of the best tutors I've ever had in terms of like just getting through stuff through my stupid head. Ensemble is. Can't find it.
I was wanting to look into that because he's also got that NBeats and implementation of that.
Oh yeah,
for forecasting. I want to dig into that a little bit. It's a little bit of a tangent, but yeah, I do need to.
Yes, it is a bit of tangent. My
Yeah,
apologies.
yeah.
Resample.
That's good.
Blue onto this. I'm pretty sure it should be in this lot, but where's the search function? Ecosystem, model time series, back to the thing. API, reference functions. Might be in that. Bayesian. Well, never mind. I'm taking too long over this. I'm gonna.
Oh, it's cool. I will take a look. I will take a look after we talk.
There is something. It's clearly not called model time Bayesian. There's a lot of the problem with Bayesian time series before. So if you wanted to do what's called a structural BSTS, Bayesian structural time series, is there weren't really many good ways to implement it, or what ways there were. They weren't very good for doing iterative forecasting.
I see.
So yeah, this is it. Bayes forecast.
Okay, Bayes forecast. Gotcha.
Yeah. So this is really cool. There's a lot of really good stuff on this. Yeah. Probably not best to go straight to that. There's the GitHub here, and down here it's got a list of some things that they do. Bayes forecast, I think it is. And it's got Garch, stochastic volatility, ETS. Some of this stuff is used as the back end for
I see.
Monte Carlo with standard probabilistic language. The aim of this package is to provide invariants for forecasting. So available models are, so it does basically the same as these, but
so it's got all your major modeling, the REMA, seasonal, all that stuff.
Yeah, these are all really cool, really cool things.
Yeah, very nice.
But like it opens that up, because one of the problems you have is that with a lot of the things like even Profit. So Profit is actually using
that's right,
in the background, and it uses local. It uses something else for local trend, and is it BSTS for the long term? I can't remember. It's one way around or another. It uses I think it uses local linear for the kind of like seasonal trends, and then it uses BSTS for the long-term trends, or the other way around. I can't remember. But yeah, it's really, really cool. And that just opens up the time series stuff a little bit to doing to using Bayesian methods. Having said that, essentially, you can ignore all that and do neural net instead, which is basically Bayesian anyway. So entirely up to you. Right. So basically they're saying, so Stan is a probabilistic program language, which is in the back end of R, which I have never really used. And I don't know how that differs from normal R language.
Yeah, if you want to get advanced class with the Bayesian stuff, you can get into Stan. I haven't gotten there myself. I'm just trying to beef up on the basics and just get a good conceptual understanding. But yeah, it's probably be interesting to explore at some point.
I mean, I imagine you've got pretty good statistical skills, to be honest, with your background.
Yeah, I studied it for some time. Yeah.
So should we just crack on this then? A wide range of response distributions are supported, allowing users to fit all different kinds of models, as we saw with the Bayes forecasting. Models can be, so basically it's the same thing, just giving us more so going back to that bit above, it's the difference between doing between creating your parameters with maximum likelihood with no real variation based on the probability of those parameters, versus doing that with simulation in order to create essentially, I suppose, stronger parameters. In which case you can basically implement anything that's basically in classical classical statistics with a Bayesian approach. Is that fair to say? So reproducing the maximum likelihood using BRM with flat priors and optimization. With flat priors and optimization, similar to standard. So they're basically, so following the data. Can you not pipe this in? Does I'd have thought it would work with what's it called, a MIGA pipe.
Yeah, probably. Maybe it does. I don't know. We could try.
Yeah. It doesn't matter what order you put the arguments in, doesn't it? You'll notice I prefer to define my data. Oh yeah, because he's just using X and Y.
Yeah.
Okay. But you'll notice that I prefer to define my data before defining my model.
Makes sense.
Even when you don't set them up yourself, BRM assigns priors to all model parameters by default. If you're ever curious about what those priors are, you can use get prior function. BRM categorizes priors into various classes. The priors of regression slope are often class B. By default, parameters class B have a prior, have a flat prior across real number line. Right. Default parameters have class B have a flat prior. Oh yeah, okay. And priors for model intercepts, however, are typically of class intercept. These default to the normal distribution wherein, oh right, okay, so the intercepts on a normal distribution, but the regression, sorry, the coefficient defaults to flat. It's interesting. Are automatically set to be wide and minimally informative. Details see the set prior function. Okay, so you might have to read that at some point.
Yeah,
later reading. Unlike with standard, BRM does not have an algorithm equals optimization that will allow for maximum likelihood estimation. If you want a frequentist estimation, BRM is of little help to you. So, I mean, that sounds like we don't, it sounds like to me what he's saying is we don't need the maximum likelihood estimation because we're using a Bayesian approach.
Right, which seems fair. There's other ways to do that. So yeah, well, you could use LM. So yeah.
If you want to fit a maximum likelihood model, that's literally what we just said.
Yeah.
Yeah. Anyway, so running the LM, you get confidence intervals, uncertainty intervals, and compatibility intervals. That's interesting. So they create fake data, which is this, which is your X and your Y, and then he does a regression. Then he does a just basic linear regression on it. Seed, I presume, is set seed argument.
Right.
Is that right?
Yeah.
Fits.
I guess it puts it out to a file. I don't know.
Yeah. Yeah. Well, we could look. I suppose we could look at that.
Yeah.
Let's look. What's
So
it called? Was it this one?
Yeah.
It's not been running the console, so it doesn't like it. I wonder if I can just access it. Right, let's ignore that for now. Let's just carry on. This, okay. Anyway, so he pulls it out anyway. So Fitz is so he saved the model. Here. 8081. Is that what we created up here?
What's that?
Did we create that up here? This other model.
Oh, yeah.
I think this model was created earlier on, and that he's using that for the data here.
He's pulling it out again, yeah.
I'm presuming.
Makes sense.
Yeah, I mean, it says fits, and it says model 08.1, so I'm presuming that's what that is. But then he's also called this model 8.1, which is slightly confusing. Anyhow, so it prints it out, and then it gives us all of this information, and it's quite bulky, and there's quite a lot of information here.
Yeah.
So I'm not really sure what all this means. So the summary includes 95% base confidence intervals.
That's good.
Of all the parameters.
Lower and upper, yeah.
Yeah, and these are listed in columns. So that's the lower and that's the upper. So we expect that to be the lower part of 95. That's the upper.
Wide range there.
Sorry?
Pretty wide range. Oh, this is fake data anyway, so.
yeah, it is. These are the same as if you were to use base quartile function, which we'll do ourselves in a bit. If you like the exact, if you'd like to extract the simulation draws from BRM, the go-to function is posterior sample. So you can pull out the posterior sample. So that's similar to what we did above earlier, isn't it? Apart from with linear, was the other one a linear model? Yeah, so we took that model and then just recreated lots of different coefficients by doing bootstrapping. If you like to, yes, there we go. And we can save those as posts, and then printed those out for us. And then that's again our, what's it called?
Is that the log of the probability or something?
No, he called it something else earlier. It was like the, not confidence, it was critical, no.
Credible?
Credible, that's it, credible interval. Yeah, so we have 3 columns named after A, B, C, and sigma parameters, respectively, as we briefly covered. Where did these parameters come from? Using the likelihood surface to assess the uncertainty of the parameter estimates. The final P1 column is outside the scope.
It's looming in the shadow.
Yeah, it's basically saying the same thing. Here's how we might hand compute the 95% confidence interval. So print longer sigma. I mean, yeah. Another handy way to get them is with posterior summary. Okay. So he's just showing us different ways to get hold of the 95% confidence interval if you want to. And I believe that's basically the end of the chapter. So essentially what they've shown us is that we can use Bayes in order to model the parameter estimates rather than just having a flat expectation of these are the parameters. And thereby, because we're bootstrapping the actual samples, we can thereby bootstrap, I suppose, or rather create different estimates of the probability. Sorry, we can create different estimates of the parameters, which is where the strength of Bayes lies. Because when we're doing frequentists, we just estimate the parameters and base those on Gaussian theory, but we don't do the same thing with the actual parameters that we're estimating. And as a consequence, we're not accounting for error in the measurement of the distribution, accounting for error in the measurement of the parameters, because our distribution is not perfect, so our parameters shouldn't be perfect either. That's the way how I'm interpreting this. Right, okay. Did you have any other thoughts about this chapter?
Not really beyond kind of what we've discussed. Yeah, I'm very interested in the BRMS stuff. I'm going to go do a little bit of reading about that, because that's not even, he doesn't use that in the book at all, but it seems like it's a useful tool, so I'm gonna have a look at that. Yeah,
I would say that I mean, I'm gonna have a look at it as well after this, but I would say that it's a really good, because it works better with the tidyverse. that is probably more useful to use in this particular case. And also because if you follow the link that I added, you can just basically go to his GitHub and pull it all out. So you've got the tidyverse code essentially available to you.
Yeah, I did pull it down into a project, so I am going to kind of explore his code too. I think this is a really good resource, so I appreciate that as a supplement to the book. So that's really useful.
It's good to have you with Steve as well, because because there are times when I get trapped on theory and ideas, and it's like I just without someone else's input, it's hard to nudge yourself in the right direction.
It's good to have somebody to talk to about the topics and everything. So it's good that you guys are doing this. Glad I was able to catch up. I got the book and caught up, so yeah, it's good.
No, it's great, to be honest. Have you did you get around to doing any of the exercises?
I have not, honestly. I really should. I was better about that with statistical rethinking, but I do need to allocate some time and just kind of dive in and explore that a little bit.
Yeah, I mean, like, sorry.
Yeah, it seems like it's similar. Like with the statistical rethinking, they would say, try this, try this, try this. So it's really mostly just a way to explore and sort of push the boundaries of maybe the things they did, and get more muscle memory and just intuition around how would I use this in practice. So yeah, I think it'd probably be value in doing that for sure.
Cool. Yeah, I mean, if I had time, I'd probably do the exercises. But one of the problems I do find with the exercises is that they don't have answers available online, so you can't check whether you're accurate. It's all very well when you're at a university and you've got a professor or a senior lecturer there to help, but it's certainly not the case here.
Go to office hours or go to another grad student, but yeah. And not to, I feel like I'm talking about statistical rethinking too much, but I will note they do have, I was able to find online, somebody had worked through all the exercises. So as I went through it, I would, check in with what they had done, or, maybe do something a little different than what they had done. So I found that to be, useful as well.
Well, in that case, I think I'm going to add that to my list of things to do, statistical rethinking. I'm pretty sure there's a tidyverse version of that as well.
Yeah.
In fact, Kurtzman probably has done that as well, because if you look at his GitHub, he's got a few books that he's done.
I will take a look at that. Yeah.
Statistical rethinking, tidyverse or tidy models. Yeah, he has done it.
He did it all. Okay, see, because I will say, and he's probably going to say the same thing. If you use the book, and this was fine to me because the book was not. I mean, it was about using R encoding to get experience with it, but the book is much more about how are these models structured, what do they mean. So if you weren't necessarily using tidy models and ggplot and whatever, it doesn't really matter. So yeah, he has his own package and he uses that throughout the book. He uses base R plotting, but yeah, as far as what the book is trying to do, I think it achieves that. So it didn't really bother me, but it would be nice to have something that was more tidyverse based. So this is good.
Yeah, I think I'm going to buy that book now because it sounds, you've sold me on it. It sounds
like I really talked to this guy and say I sold your book for it. No, why help you sell book?
And his lectures are free online as well. I mean, that's great.
I did see that. I've watched a couple of them. Yeah, they're good.
Yeah, well, I'm definitely going to give that a go. This has been really great, Steve. It's really good to talk to someone, and also, I've talked to Pavarita as well. And it's just good to have someone at the other end of the line, but also like another person's thoughts on the books as well is always helpful, particularly because you've got a good maths background as well. I think that will certainly help.
Yeah.
And also your addition, having read the statistical rethinking, really, really excited to get a bit further with this now. and just crack on.
I feel like, yeah, it did help me, like I say, just get a better understanding of one, what's the Bayesian approach, what are you doing when you're doing the Markov chain, Monte Carlo sampling? How do you know if you did it right? Things like that. So it was a very good book.
Yeah, I was just thinking, like, until we just went through that last part of this chapter now, I didn't really understand the Bayesian approach properly until like that very moment of, oh, we're actually giving error to the parameters by bootstrapping it. And so that's, when you think about it, it makes a lot of sense. But when you've beforehand, it's just kind of like, hadn't been a thought in my head.
Yeah, it's kind of like bootstrapping, but it's yeah, I probably can't really do justice to it, but yeah, if you look into like things like the Metropolis algorithm, or just how does MCMC work, it will give you a little bit of a better sense of what they're actually doing there, and kind of how they navigate that whole sampling process. But it's similar in the sense that you're doing simulations, right? So you're kind of building your model of the world with the computer, and then you have the data that you can then use and say, okay, the distribution looks like this. What does this mean? Yeah, so it's a way to get a handle on things when you don't have a straight analytical solution to it. So yeah. Which is kind of what the whole Bayes thing is, to my understanding. There's a good book that's not technical, but it's interesting, called The Theory That Wouldn't Die. So if you ever just want kind of an interesting book to read, it's kind of like the history of the Bayes, theory, and how, we all know it originated centuries ago and was kind of frowned on. And to a certain degree was intractable until we had powerful computers, and we could use these techniques, because there are some cases where you could do the integrals and it's great, but most of the time no. So yeah, so it's just interesting to, it gives the background of how the theory was used and how it evolved. So that's my other book recommendation. I've got all kinds of book recommendations.
I'm busy. I'm trying to learn so many things at the moment.
Yeah, I know. It's that thing where sometimes I will have like a stack of books. It's like I just need to choose one or two books and just get through them.
Well, you say that, but I'm if you're anything like me, you're probably reading about 10 different books, and you're only about six chapters into each of them.
Yes.
I'm also about to start doing statistical learning. Introduction to Statistical Learning.
That's a good one. Yeah.
Second edition, and it's I've already read it, but like, I mean, I've got to go back over it again now because I've introduced another area to it. But I mean, at the same time, I'm having to learn a lot more about neural networks just from work, and it's like, trying to stay on top of all that, and also the really cool stuff is the news things like GAN and transformers.
Oh yeah, transformers I'm looking into recently, because the NLP applications there are interesting for sure.
Yeah, absolutely. It's just like, I mean, I'm just looking at them in general, really, but because there's always time series applications to these things as well, and it's always just like, it's really, really cool, but it's really complicated. I find it really hard.
You gotta have kind of a focus.
Yeah, well, yeah, I mean, this is the thing about doing data science, isn't it? You end up having, if you're not a unicorn, you eventually will be one. Right. Or I hope so, or I die trying.
Yeah.
Anyhow.
That's right.
Right. Anyway, Steve, I've got to go. It's been great talking to you. Sure. Hopefully see you again next week.
Yeah, I'll plan to be here and make it a regular thing. Yeah, okay, it's good talking to you as well.
Okay, thanks, Steve. Bye-bye.
Talk to you later. Bye.